Today we will talk about one variant of k-mean clustering approach, and that was lately introduced in 2000 is something called is the bisecting k-mean, and the performance of bisecting k-mean is much better than the k-mean clustering. Okay. How it works? We already learned the k-mean clustering. Okay. So, output of the k-mean clustering is a k clusters. Okay. So, bisecting k-means means it will form two clusters, but if we want to find, we see if we have the information that there are 6 clusters. So, how do you proceed? So, you see the algorithm here. So, initialize the list of the clusters L. So, first you consider the entire data set is a single cluster. So, that is first it is this is one cluster and you consider this is C1 and then you put in a list. So, that list initially consists of a single cluster. Now, remove a cluster from the list of clusters. So, there is only one cluster, you remove the cluster. So, then this will be null. So, there will be no cluster here, first situation. Now, what you do is you do it bisect the selected cluster using k-mean clustering method for a number of times. So, first you consider the entire data set is a cluster. So, first you have a list. So, entire data set C and then C1 is equal to the data set. Next you remove from here. So, this will be null. Okay. So, this will be null, and now entire data set, you got the entire data set and you apply the k-mean clustering, and what is the value of k? K equal to 2. So, then you will get a cluster, let us say C11 and C12, and you apply a number of times, let us say 10 times or 12 times or 15 times you apply the k-mean. So, on the same cluster, that is same data, here in this first example C1 cluster. So, then you will get the result C, let us say 21 C22. Another time you apply C31 and C32. Each time you will get the 2 clusters. Then you apply C41, C42 and so on. And for each clustering, this is something called clustering in together. For each clustering you compute the SSE, sum of the square error. We know how to compute the sum of the square error. For each case we compute the SSE. Let us say this is SSE 1, this is 2, SSE this is 3, SSE this is 4 and so on. And you choose a clustering, not cluster, you choose a clustering however SSE value is minimum among the clustering. So, select 2 clusters, that means each clustering gives 2 clusters. Select 2 clusters from a bisection with lowest total SSE. So, you apply the k-mean with k equal to 2 many times, and each clustering means apply the k-mean one time and you find the 2 cluster and compute the SSE. Again from with 2 different initial point you compute, you apply the k-mean, you will get the 2 clusters and you compute the SSE, and among these all clustering, each clustering will give the 2 clusters and 1 SSE value. Wherever the SSE value is minimum, you consider that clustering. So, that 2 cluster you add to the list here. What is the list? Length is null, because you have taken out, you have removed 1 cluster. Now, there is no cluster here. So, now your list will have 2 cluster, let us say some C1 and C2. Add these 2 cluster to the list of the cluster L until the number of cluster in the list L is k. Say suppose k value you have taken k equal to 5. So, number of cluster is 2. Then again you have to repeat this step. What is this step? Remove a cluster from the list of clusters. So, from C1 C2 again you take out 1 cluster. So, let us say you take out C1 and again you partition it using bisecting k-mean many times and you choose the minimum SSE. So, you will get 2 clusters. You have to choose a clustering consist of 2 clusters, because every time you are using the same k-mean where SSE value is minimum. So, you will get 2 cluster, you add these 2 cluster into the list. Earlier you had 1 cluster, now you add another 2 cluster here. So, number of cluster will be 1 more. So, it will be 3. So, in every iteration you will add it 1 by 1 cluster. So, then your list is C1, C2 and then C3, but is 5, you need 5. Again you take out one of the, you remove one of the clusters and apply the bisecting k-mean for many times, and you choose a clustering, because bisecting k-means each clustering will have 2 clusters, and you choose a clustering wherever the SSE value is minimum, and then you add it here. Earlier it was 3, you remove 1, so it become 2 and you add 2, so it become 4 now. Again you take out 1, apply the same k-means many number of times and you choose a clustering and you add again 2. So, it become 4, you take out 1, so now is 3, 3 plus 2 5. So, you reach the number of cluster 5. So, that is the final output. Obviously, complexity will be much better than the, more complexity will be not better, complexity will be more than the traditional k-mean. So, what happened? What you can see eventually. So, you had one big cluster, that is the data set D, then from you got the 2 clusters and then you added to the list. So, you had 2 cluster, now this cluster you removed, and then next level you got again same cluster here. So, you got 3 clusters, any one of them, again you divided it, this is 1, this is 1. So, you got 1, 2, 3, 4, again you divide any one of them. So, maybe here, and then you will get total 5 clusters. So, you will get a hierarchical clustering, but finally you will concentrate here. So, this is the final results here. So, while talking about the k-mean clustering, we said the SSE value. So, that is the SSE, we have to optimize the SSE value. What is the objective? To get the minimum SSE value for a k number of clusters, and then how we said we compute the SSE value is something for each clusters and then sum this value and then we will got this one. Okay. So, this can be seen as the optimization problem, and for the simplicity what we consider, we will compute the squared Euclidean distance. Here is like squared Euclidean distance. What is Euclidean distance? Is like SI minus YI square summation over this one, right. So, what we do it? We consider this one is the measures, and for simplicity what we consider. So, this is the distance. So, distance is defined at, this is summation over all dimension I equal to 1 to d xi yi square, and not only that, we consider I equal to d equal to 1. So, it is a single dimensional data. So, easily it can be extended to multi-dimensional. Okay. So, in that case what will be that formulation? So, formulation will be minimize the SSE value, minimize the SSE value for all cluster I equal to 1 to k capital here. Okay. I equal to 1 to k. So, you have a k cluster, let us say, and summation over each data point, summation over each cluster. For each cluster what you have to do, you have to compute a point and you have to compute the distances. Now, you have to identify what is that point. We know this is a centroid earlier. So, but now we will see formally, you consider a point from where the all other distances will be minimum. So, you consider that point and we finally prove that point is nothing but the centroid. So, this is we have to minimize, that means for minimization what you have to do it. So, we have to find the point within a center. So, we need to differentiate with d I by d, let us say C k, we have considering only one cluster C k. So, this k is smaller. Okay. And then what you have to do, you have to compute SSE and this should be 0. So, then we can write it del del C k, scale is smaller here, okay. Summation over I equal to 1 to I equal to 1 to capital K, summation over x C, let us say C cluster C I into, this is the point C, small c I, minus x square, okay. So, this is okay, let me write, this is, we want to find the point C, and this is the point C I within a cluster C, and this is a cluster C I, this is a capital C, okay. Now, what you have to do? You have to consider this value is 0, and we are considering with the kth cluster, because we have the k cluster, and let us say first we are computing with respect to the within a cluster where should be the point that minimum distance will be minimum, and that will contribute to the total SSE value, okay. So, therefore, what you can do it from here. So, summation over I equal to 1 to capital K, that is the k number of cluster we are considering, then summation x, that is cluster C I, del del C k into, this is actually we are considering cluster key C k. So, then this is C k minus x square, and this is no longer I. So, this is a C k cluster, kth cluster, and that should be 0, and for all other cases we are not considering. So, this sum you can cancel out, okay. So, then what we got it, summation over del del smaller c k, because this is a point, with this point we are differentiating, into c k, this is also smaller, minus x square is equal to 0. Now, if you differentiate here, so here what we will get it here, c k minus x square, and with differentiating with c k. So, therefore, 2 into summation over 2 into c k minus x, okay, equal to 0. Okay. From here we can write it, what we can write it, summation over c k minus, this is smaller c, c k minus summation over x, summation over the points, summation over the point x c cap, this is a cluster, kth cluster x minus c k, okay. This should be 0. So, from here what you can write it, summation over x c k equal to summation over x where x belongs to cluster c k. So, from here this is summation over the point x, but here inside there is no point x, okay. So, then you can write n into c k is the point, that is n into c k equal to summation over x, x is c capital X, okay. So, then here you can write c k, that is the point we are searching, equal to 1 by n into summation x, where x is okay. So, c k is nothing but the centroid, that is the all points summation divided by the number of points. So, here this point is nothing but the centroid. So, we are trying to find a point wherever the SSE value is minimum, and it found that point is nothing but the centroid of the each cluster. So, similarly, here if you consider the SSE value is nothing but L1 distance. So, if you consider the distance earlier we considered this distance is summation over x I y I square where I equal to 1 to d. Now, if you consider the distance is nothing but the L1 distance, L1 distance is nothing but this one. So, therefore, SSE value will be summation over I to k. So, k is the total number of clusters and the x belongs to class C I and C I minus x j. So, you have to find what is C I. For simplicity, what you can consider, this is a one dimensional case. Same way, what you do it, del del C k smaller c k of SAC sum of the error. So, this will be sum of the absolute error. So, this is sum of the okay, this should be 0. Okay. So, therefore, same way you can write delta del C k summation over x belongs to C k cluster, we can write C k minus x, this should be 0. So, what will be the derivative of this part? So, we define mod x equal to x if x is greater than 0, mod x equal to minus x if x less than 0. So, therefore, if you C k minus x is greater than 0, then we can write C k minus x, and if you take derivative of del del C k of C k minus x, so this will be 1. Now, if you take this value, that means x minus C k, x is greater than in this case minus x. So, if you put minus x here, so minus minus plus, so x minus C k. So, if you take the derivative of del del C k, you will get minus 1. So, now if you take the summation of plus 1 minus 1, you will get 0. So, plus 1, some cases minus 1, plus 1, minus 1, plus 1, minus 1, you will get the value 0, because summation of these all derivative values will be 0. When this will appear? So, that is number of plus 1 and number of minus 1 is same. So, that means actually if you have a clusters here and you have a set of points here, you choose a point, on the left side there will be on left side and right side there will be equal number of points if you assign the points in that way. So, in the other way around, so this is nothing but the median of the all data points. Let us say example 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So, this is median is here. Okay. So, 1, 2, 3, 4, median is somewhere here. Okay. So, now you do it, this is C k and these all are x, these all are x. Now, you C k minus 1, so 5 minus 1, so this will be plus 4. However, C k minus 9, so 5 minus 9 it will be minus 4. Similarly, this will be plus 3, this will be minus 3 and so on. So, ultimately what you will get, this is the original values, ultimately this represent that this is nothing but the median of the distribution. So, median of the distribution is nothing but the, if you take the multidimensional, so it is nothing but the centroid. So, next we will talk about something to speed up the k-mean clustering algorithm. So, if we move back, k-mean clustering, if you see here k-mean clustering. So, what we found in k-mean clustering, we initially choose some set of points here, okay, that is the initial k points, and now for the all set of points we compute the distance from x1 to the this centroid, this centroid, this centroid and this centroid, that is we do, and wherever the distance is minimum we assign to the closest clusters, that is the k-mean algorithm. So, initially we take the k centroid and we compute the distance from the each point to the k centroid point. So, therefore, how many distance we compute? So, if there are n number of points, for each point we compute the k distance. So, therefore, in single iteration we compute the distance n into k, k is the number of clusters. Now, Elkin in 2003 paper published in ICML. ICML is one of the top conference. Okay. Paper published, but idea is very simple, and he said ki there is no need for doing computation from the point, each point from here to the all centroids. So, let us say if we use the k-mean as a pre-processing step, you have a, let us say you have a say 10 million data and k value is say let us say 1000, because you are using k-mean as a pre-processing step, you can consider, because this is not the final pre-processing, you will have a some sophisticated algorithm on the top of this one. So, for each point you have to compute the distance 1000 and then what there will be 10 million. So, 10 million means 10 into 10 to the power 6 and then 10 to the power 3. So, these many distance computation you have to do. He said, can you reduce the distance, number of distance computation, and number of distance computation complexity depends on the dimension. If you have a 1000 dimension and you have a 2 dimension, obviously that will make a huge difference. So, therefore, he focused how to reduce the distance computation in some scenario, that is the paper all about. So, triangle inequality to accelerate the k-mean clustering approach. So, he used the property of the metric space property. As we studied earlier, the metric space property means it satisfies 3 conditions. So, distance function will be distance from x to x will be 0 and always distance of any point x to y greater than equal to 0, and it should be symmetric, distance from A to B is same as distance from B to A, distance from Kolkata to the Delhi same as the Delhi to Kolkata, and distance from A to B plus distance of B to C, A to B, B to C is greater than equal to distance from A to C. So, that is something called triangle inequality. So, what he said, we can avoid some distance computation using this theorem. How? Let us say here. So, we have a point here, we have a centroid here, there are 2 centroid B and C, and we have a point x. We are trying to find whether point will be assigned to B or C, any one of the centroids. Say there will be multiple centroids. So, we can generalize that. First we think of there are 2 centroid B and C and there are point x. So, we computed the distance from x to B, we know this distance, and obviously, when centroid is from, this was also computed C to B, otherwise we can compute the distance from B to C. So, we know this distance here. Now, we will estimate what can be the value of x to C without computation. Not only that, we won't estimate actually. What we conclude that if distance from B to C is greater than the distance twice of the distance from x to B, then this x cannot be assigned to C, because distance x to B is much closer than the distance from x to C. I repeat this. There are 2 centroid B and C, we know the distance from centroid to centroid, and we computed the distance from x to B, we know this distance. Now, challenge is can we avoid this distance computation? If we can avoid, so if we go more for another points here, similarly can we avoid this second centroid, say let us say C1 and so on. So, in that way we can reduce the number of distance computation in k-mean. So, what is they said ki if distance from B to C is greater than the twice of the distance from x to B, then no need to compute this distance, because this distance is greater than the distance from x to B. So, the point x is closer to the centroid B. So, we can assign the point x to b. So, there is no need for computing distance from x to c. So, just we will compare this value and this is pre-computed. So, this time will be 1 unit, but if it is a 1000 dimension. So, you need to have the 1000 unit time for spending the time computation, that is their theorem. So, how they got this theorem, that is we will see here. So, from tangent equality what we can write, distance from x to c plus distance from x to b, we can write distance from b to x plus x to c is greater than equal to distance from b to, we can write this one distance from x to b plus x to c. So, we write b to x instead of b to x, x to a, we write, I wrote it x to b, and x to c we write distance from x to c is greater than equal to distance from b to c. We can write, there is no confusion from the triangle inequality. Distance from here to here and distance from here to here is always greater than the distance from b to c. Now, simply distance from x to c plus distance of x to b is greater than equal to distance of b to c. What is the distance of b to c? You just simply replace distance of b to c is always greater than equal to distance of x to b. So, we can write here 2 distance of x to b. From here you can write distance from x to c greater than equal to, we can take out it here. So, then distance of x to b. So, therefore, if you know this distance, you know this distance, you can compare, and if does not satisfy, in that case you have to compute the distance, there is no other choice. But if this satisfies, then you can avoid many distances.